So since the advent of AI, we have slowly made a change on how we come across to our clients. We have moved from being a system integrator to becoming an AI builder. So this is all about taking the various aspects of AI, making it production grade, making it enterprise ready, making it trustworthy as well as safe to use, and being able to drive that adoption at scale. So to do that, you have to be able to use not only what we create internally at Cognizant, but also use the best of breed applications that are created by our ecosystem partners. Our AI labs are powerful areas where great ideas around AI come from. Once we get some of these great ideas and we realize that these need to be applied to our clients at an enterprise scale, they come into the AI app products and platforms group. What we do at that point is we want to make sure that these applications are built in such a way that they are enterprise ready, they are safe, we build the right guardrails around them, and then they're able to scale. So what we're then able to do is take something that is absolutely enterprise ready and implement these great ideas within our clients' IT landscapes.
GenAI is good at answering single questions or performing single tasks, but most business operations aren't just one question or task. They're a series of questions or tasks where each one depends on the output before it. Errors then compound. If step 2 is wrong, step 3 is built on that wrong answer, and by step 8, the entire output is unreliable. Some large language models can handle tasks with a handful of steps, but go off the rails with more complex problems. With some business processes requiring hundreds or even thousands of steps, this becomes infeasible for current LLMs to solve. Maker fixes this by breaking a large task into tiny pieces. Each piece gets a dedicated microagent that only sees what it needs to see, nothing else. If it produces an error, that error gets caught and corrected right there before it can spread. There's also a built-in detection system called red flagging. If an output looks structurally unreliable, it gets discarded before it can influence anything downstream. To prove it works, we ran Maker on a puzzle that required over 1 million correct moves in a row. Maker completed every single step without making a mistake. Regular LLM models fail to complete even hundreds of correct actions in a row, making this advancement a huge leap forward for real-world business applications.
By embedding Maker into NeuroAI Multi-Agent Accelerator and the AI systems we built for clients, we significantly improve the reliability of these systems, enable rapid prototyping of scalable and extensible networks of agents, and also improve the cost efficiency. The real enterprise challenge Maker addresses has to do with sustaining coherence across workflows. Take, for example, clinical workflows like triage, care plan coordination, prior authorization, utilization reviews, and discharge planning. These are multi-step because the agents have to gather facts, reconcile records, apply policy, identify exceptions, and make a recommendation, remaining consistent from start to finish. One wrong decision early on can corrupt the whole chain. Maker allows us to build such systems reliably. There's also a self-healing benefit. If a specific agent makes a reasoning mistake or hallucinates, the error correction in Maker catches it and corrects it instantly.
Traditional software is predictable. Same input, same output every time. GenAI is not. Asking the same question on 2 different days and you may get 2 different answers, or a completely fabricated one. That unpredictability is the primary reason companies don't trust AI enough to deploy in critical processes. We developed a mathematical way called Semantic Density to score how trustworthy an AI response is right at the moment it's produced. It works by using a judging mechanism. Based on the consistency of the AI's output, it can tell whether or not the answers are likely to be correct. More specifically, the system looks at the meaning behind multiple possible responses to the same question. The idea is simple. If many independently generated answers cluster around the same meaning, the answer is more trustworthy. But if the answers are scattered across very different meanings, that signals higher uncertainty. The scoring happens in real time before the response ever reaches the person or triggers the next step in the workflow. So instead of simply hoping the AI produced the right answer, you have a measurable confidence scores that tells you how much to trust the output.
Measuring an agent's confidence is a way to assess the likelihood that an AI response is correct at the moment it is produced, rather than just hoping the model got it right. That is important because one of the biggest reasons AI stalls in enterprises is when it operates in spite of having low confidence. The practical benefit is that clients can use AI in higher value, higher stakes processes because they have a real-time mechanism to monitor an agent's decision confidence before acting on it.
As enterprises move from isolated AI use cases to systems with many agents working together, coordination becomes a fundamental challenge. Most systems rely on a central boss agent to manage how work is distributed. That boss becomes a bottleneck, and if it fails, the whole system fails. Our prompting protocol for agents takes a different approach. Instead of centralizing control, coordination is distributed across the agents themselves. Each agent has two sides: a coordination side that communicates with other agents and determines how work should be handled, and a specialist side that focuses entirely on executing its specific task. This allows agents to dynamically decide which other agents should handle a request, rather than relying on a fixed controller. Because of this, the system becomes more resilient. If one agent goes down, the others simply route around it, and there's no single point of failure. As new agents are introduced, the network can recognize their capabilities and incorporate them naturally. The result is a more scalable and adaptive way for large networks of AI agents to work together.
This agentic architecture enables greater adaptability, resilience, and extensibility in multi-agent networks. Because it's decentralized, if one part goes down, the rest of the network just routes around it, so there's no single point of failure. It's also expandable. You can plug in a new specialist agent, and the whole network instantly knows how to use it, with no re-engineering. Agents using this coordination mechanism can even collaborate in real time to redesign the user experience based exactly on the user's context and what they are trying to do. For clients, this architecture is useful anywhere they want AI to handle work that is cross-functional, exception-heavy, dynamic, too complex for one monolithic agent, or changing too fast to hand script every workflow. So it enables clients to build agentic operating models rather than isolated AI features. For example, a customer issue may require billing analysis, policy review, entitlement checks, fraud screening, logistics visibility, and next best action decisions. Instead of one giant agent trying to do everything, the work is dynamically and spontaneously routed across specialized agents.